Hey friends, welcome to the YouTube channel all about electronics. So in this video, we will understand that how to design a finite state machine, and we will understand it by taking the example of the sequence detector. And in this video, the sequence detector which we are going to design is of Mealy type. So first, let us see the steps for designing the finite state machine. So first of all, define the purpose of the machine in the simple words or in form of the block diagram. That means how the machine works and what are the inputs and outputs of the machine. And of course, it should be realizable using the finite number of memory elements. So then after based on that, draw a state diagram of the machine. And once we have a state diagram, then we can draw a state table from the state diagram. And once we get the state table, then check for the redundant states in the state diagram. And if there is any redundant states, then remove it from the state diagram. So in the previous video, we have already seen that how to remove the redundant state from the state diagram. So after removing the redundant states, the next step is to select the type of the flip-flop which we are going to use in the circuit. So it can be either D flip-flop or JK flip-flop or even SR flip-flop. So once you have selected the type of the flip-flop, then the next step is to draw the excitation table of the flip-flop to get the required transitions. And after that, find the boolean function of the flip-flops in terms of the state variables and the inputs. And similarly, also find the boolean function of the output in terms of the state variables and the inputs. So once we get the boolean function, then from that, draw a logic circuit for the machine. So by following these steps, we can design any finite state machine. So using these steps, now let us design a sequence detector which can detect the 1001 sequence. So first of all, let us understand what is a sequence detector. So a sequence detector is a digital circuit which detects the specific bit sequence in the received incoming bits. So for example, if the sequence detector detects the 1001 sequence, then in the received bits, when the 1001 is received, then the output of the detector will become 1. Now in the sequence detector, we have two types, that is the overlapping and the non-overlapping. So in the overlapping sequence detector, the last few bits of the sequence can be the first few bits of the next sequence. On the other hand, in the non-overlapping sequence detector, once the sequence is detected, then the detector gets resets and it starts searching for the new sequence. So let us understand both types of sequence detectors through one example. So let's say this input is applied to the overlapping sequence detector which detects the 1001 sequence in the received bits. So if we see the output of the detector, then this is how it will look like. So here, when the 1001 is received in the sequence, then the output of the detector will become 1. So as you can see, for the first 3 bits, the output of the detector will remain 0. And as soon as the last correct bit in the sequence is received, then the output of the detector will become 1. Now like I said, in the overlapping sequence detector, last few bits of the sequence can be a first few bits of the another sequence. So here, this last one is the starting bit of the another sequence. That means once again, the output of the detector will become 1 after this 001. So once again, this last one can be a starting bit for the another sequence. And as you can see, the output of the detector will become 1 over here. And once again over here, the output of the detector will become 1. So basically in the overlapping sequence detector, the last few bits of the sequence can be the first few bits of the next sequence. While in the non-overlapping sequence detector, that is not the case. That means once the sequence is detected, then the detector will get reset and it will start searching for the new sequence. For example, if the same input bit stream is given to the non-overlapping sequence detector, then this will be its output. So as you can see, once again the output of the detector will become 1 whenever it receives this 1001. And until then, its output will remain 0. But since it is a non-overlapping type detector, so a part of the sequence cannot be a first few bits of the next sequence. And here, the detector will start searching for a new sequence all over again. That means once again, the output of the detector will become 1 when a new 1001 sequence is detected. That means it will become 1 over here. And this is how the overall output of the detector will look like. So that is the basic difference between the overlapping and the non-overlapping sequence detector. So in this video, we will design both overlapping and the non-overlapping sequence detector which will detect the 1001 sequence. And both the sequence detectors will be of Mealy type. So first, let us design the overlapping sequence detector which detects the 1001 sequence. So as you know, the first step is to draw the state transition diagram. So in the sequence detector, we will have a one input and the one output. And since it is a 4-bit sequence detector, so it will have total 4 states. So here, this state A is a starting state when no correct bits in the sequence is received. Similarly, this B state is the state of the machine when the one correct bit in the sequence is received. And likewise, the C is the state of the machine when the two correct bit in the sequence is received. And likewise, this D is the state of the machine when the three correct bit in the sequence is received. And after that, when the fourth correct bit in the sequence is received, then the output of the circuit will become 1. So in short, when we are designing a Mealy type sequence detector, then the number of states in the detector is same as the number of bits in the sequence. So now, since we know the input and output and the number of states in the machine, so let us draw a state transition diagram of the machine. So like I said, in the detector, we will have total 4 states. And initially, the circuit will be in the A state. That means this A state is the starting state. So here, since we have only one input, so in the each state, we will have only two possible outgoing transitions. So let us see what happens in the each state when the input is either 0 or 1. So if the circuit is in the A state and if the input is equal to 0, then it will remain in the same state and it will wait for the next correct bit in the sequence. But if the input is equal to 1, then it means that the detector has received the one correct bit in the sequence and therefore it will go to the B state. And now it will wait for the next correct bit in the sequence. So in both the cases, the output of the circuit will remain 0. And in fact, until we receive the correct sequence, the output of the circuit will remain 0. So here, this bit next to the input or the bit in the green color represents the output of the detector, while the bits in the pink color represents the input. So now in the B state, when the 0 is received, it means that the circuit has received the two correct bit in the sequence and therefore the circuit will move to the C state. But on the other hand, when the input is equal to 1, then it will remain in the same state because this new received 1 is the first bit of the sequence. Therefore, the machine will remain in the same state. So similarly, let's see what happens in the C state. So here, the C is the state of the machine when the two correct bit in the sequence is received. So now in this state, if the input is equal to 0, it means that the circuit has received the new correct bit in the sequence and therefore it will go to the D state. On the other hand, if the input is equal to 1, then it will move to the B state because after 1 0, when the 1 is received, then it is not part of the sequence. But this received 1 can be a first bit of the sequence. Therefore, the machine will move to the B state. So similarly, now let us see what happens in the D state. So this D is the state of the machine when the three correct bit in the sequence is received. So now, when the input is equal to 0, then the machine will move to the A state because this new received 0 is not a first bit of the sequence and therefore the circuit will move to the A state, that is the starting state of the machine. But on the other hand, in the D state, if the detector receives the 1, then it has received all the bits of the sequence and therefore the output of the detector will become 1. And now, since it is an overlapping sequence detector, so the last few bits of the received sequence can be a first few bits of the next sequence. So in this case, this last received 1 can be a first bit of the new sequence. And therefore, the circuit will go to the B state. So this is the state transition diagram of the overlapping sequence detector which detects the 1001 sequence. So now, from the state diagram, let us draw a state table. So as you know, in the state table, we will have the present state, the next state, the input and the output. So as per this state diagram, when the circuit is in the A state and when the input x is equal to 0, then it will remain in the same state. But when the input is equal to 1, then it will move to the B state. And in both the cases, the output of the detector will remain 0. Likewise, when the circuit is in the B state and when the input is equal to 0, then it will go to the C state. And similarly, when the input is equal to 1, then it will remain in the same state. And once again, in both the cases, the output of the circuit is equal to 0. And likewise, we can write the remaining two rows in the table. So if required, you can pause the video and you can verify the table by yourself. So now, if you see the state table, then in the first and the last row, we are getting the same next states for the x is equal to 0 and 1. But if you see their outputs, then their outputs are different. That means here, none of the states are identical. And therefore, there is no redundant states in the state diagram. So now, let us do the state assignment. So here, since we have a 4 states, so it can be represented using the 2 bits. So let's say that is equal to Q1 and Q0. So here, let's say this A is equal to 0, 0, while B is equal to 0, 1. And similarly, this C is equal to 1, 0, and D is equal to 1, 1. So based on this assignment, we will find the logic circuit. But if you use the different assignment, then the final logic circuit will be slightly different. But here, with this state assignment, this is how the table will look like. So now, the next step is to select the type of the flip-flop and find the excitations for the each flip-flop. So for that, first let us represent the same state table in the different way. So here, this X input is also represented in the separate column. And let's say the 2 bits which represents the state of the memory elements are Q1 and Q0. And here, this Y represents the output of the circuit. So like I said, we need to decide which type of flip-flop we are going to use in the design. So here, let's say we want to design this circuit using the D flip-flops. So here, since we have a 2 bits, so we will require 2 D flip-flops. And let's say that is equal to D1 and D0. So now, to go from the present state to the desired next state, let us find the required excitations for the each flip-flop. Or in other words, let us draw the excitation table for the circuit. So as you know, for the D flip-flop, the output is same as the input. That means whatever output that we want in the next state, the same should be applied as an input to the flip-flop. So here, the inputs to the D flip-flop are same as the required next state. So in this way, we also found the excitation table of the sequence detector. So now, the next step is to find the algebraic expression of the inputs of the flip-flop in terms of the input X and the present states Q1 and Q0. Because by applying these inputs to the D flip-flop, we will get the required next state. So first of all, let us find the algebraic expression of the D1 in terms of the X, Q1 and Q0. So as you can see over here, this D1 is equal to 1 for the 2 input combinations. That is when X and Q1 is 0 and this Q0 is equal to 1. Similarly, this D1 is 1 when the X is equal to 0 and Q1 and Q0 is equal to 1, 0. So here, let us write them in the K map and let us see whether we can further simplify them or not. So here, both the minterms are represented in the K map. And as you can see, they cannot be grouped together. So we can say that this D1 is equal to x bar dot Q1 bar dot Q0 plus x bar dot Q1 dot Q0 bar. So similarly, now let us find the expression of the D0 in terms of the X, Q1 and Q0. So as you can see over here, this D0 is equal to 1 for the 5 input combinations. So first, let us represent them in the K map and let us try to find the simplified expression of the D0. So here, these 5 minterms for which this D0 is equal to 1 is represented in the K map. So as you can see over here, we can make the group of 4 ones. And similarly, we can also combine these 2 minterms. So in this way, by making these 2 groups, we are able to cover all the minterms in the K map. So here, this group corresponds to X. And likewise, this group corresponds to Q1 dot Q0 bar. That means if we see the overall expression of the D0, then that is equal to X plus Q1 dot Q0 bar. So similarly, let us find the expression of the output Y in terms of the X, Q1 and Q0. So if you see over here, then this Y is equal to 1 only for the one input combination. That is whenever the X, Q1 and Q0 is equal to 1. So we can say that this output Y is equal to X dot Q1 dot Q0. So in this way, we got the expression of the D0, D1 and the output Y in terms of the X, Q1 and Q0. So now, once we got the Boolean expression, then the last step is to draw the logic circuit of the machine from the Boolean expression. So as per this Boolean expression, this is the logic circuit of the overlapping sequence detector which detects the 1001 sequence. So at the end of the video, I will also show you the simulation results for the designed circuit. And through the simulation results, we will verify that whether our designed circuit works properly or not. But now, similarly, let us design the non-overlapping sequence detector which detects the 1001 sequence. So in the overlapping sequence detector, like I said, the last few bits of the sequence can be a starting bit of the new sequence. But in the non-overlapping sequence detector, once the sequence is detected, then the detector will get reset and we will go to the starting state. So this is the state diagram of the overlapping sequence detector. And similarly, if you see the state diagram of the non-overlapping sequence detector, then there is only one difference. So as you can see, once the sequence is detected, then detector will get reset and it will go to the starting state. That means here, it will go to the A state. On the other end, in the overlapping sequence detector, once the sequence was detected, then it was going to the B state. So that is the only difference between the two state diagrams. And if you see the rest of the transitions, then that will remain same. So based on the state diagram, this is the state table of the detector. And if you compare it with the state table of the overlapping sequence detector, then there is only one difference over here. Because here, instead of going to the B state, the machine is going to the A state. So as you can see over here, there is no redundant states in the state table. That means here, we will have total 4 states. And to represent the 4 states, we will require at least 2 bits. So here, we are going to use the following state assignment. That is A is equal to 0, 0, while the B is equal to 0, 1. And likewise, the C is 1, 0, and the D is equal to 1, 1. So based on this state assignment, let us find the logic circuit of the detector. And based on this assignment, this is how the state table will look like. So here, let's say the output of these memory elements is equal to Q1 and Q0. So here, the same state table is represented in the different way. So as you can see over here, this input X is represented in the different column. So here, this Q1 and Q0 represents the present state of the flip-flop, while the Q1 plus and the Q0 plus represents the next state. So once we have a state table, then we need to decide the type of the flip-flop which we are going to use in the design. So let's say we are going to use the D flip-flops. So here once again, to represent the 2 bits, we will require the 2 flip-flops. Let's say that is equal to D1 and D0. So now we need to find the required excitations for the flip-flop to get the desired next state. Or in other words, we need to draw the excitation table of the circuit. So once again, for the D flip-flops, the output is the same as the input. That means here, to get the desired next state, the input to the flip-flop should be same as the next state. So the same thing is shown over here. So now, once we have an excitation table, then we need to find the Boolean expression for the inputs of the flip-flop in terms of the X, Q1 and Q0. So first, let us find the expression of the D1 in terms of the X, Q1 and Q0. So once again, as you can see, this D1 is equal to 1 for the 2 input combinations. So once again, let us represent them in the K map and let us try to find the simplified expression of the D1. So here, both the minterms are represented in the K map. And as you can see over here, we cannot group them together. That means here, the expression of the D1 is equal to x bar dot q1 bar dot q0 plus x bar dot q1 dot q0 bar. So similarly, let us find the expression of the d0. So here, this d0 is equal to 1 for the 4 input combinations. So all 4 minterms are represented in the k-map. So here, we can make the group of these 2 minterms. And similarly, we can also combine these 2 minterms. So here, this group corresponds to x dot q1 bar. And likewise, this group corresponds to q1 dot q0 bar. That means if we see the overall expression of the d1, then that is equal to x dot q1 bar plus q1 dot q0 bar. So in this way, we got the expression of the d0 and the d1. So similarly, now let us find the expression of the output y. So as you can see over here, this output y is equal to 1 only for the one input combination. That is whenever this x, q1 and q0 is equal to 1. So we can say that this output y is equal to x dot q1 dot q0. So in this way, we got the expression of the d0, d1 and the y. So now, based on the Boolean expression, let us draw a logic circuit of the sequence detector. And this is the logic circuit of the non-overlapping sequence detector, which can detect the 1001 sequence. So in this way, by following these design steps, we can design any sequence detector, or in general, we can design any finite state machine. So now, let me show you the simulation results for both overlapping as well as the non-overlapping sequence detector. And through the simulation, let us verify that whether our designed logic circuit works properly or not. So first of all, let us see the simulation of the overlapping sequence detector. So based on the Boolean expression that we got for the overlapping sequence detector, this is the logic circuit for the detector. So here, this first flip-flop is the D0 flip-flop, while the second flip-flop is the D1 flip-flop. And here, through the parallel in serial out shift register, the 16 bit of serial bit stream is applied as an input to the detector. So as you can see over here, the input bit stream is equal to 0001, 0010, 0100, 1000. And since it is a serial shift register, so this bit stream will be applied to the detector from the right side. So from the right side also if you see, then this sequence is 0001, 0010, 0100 and 1000. So as you can see for this sequence, the output of the detector should become 1 for the 3 times. So now let me just run the simulation and let me show you the output waveform. So first of all, let me just zoom the all waveforms. So here, first I am clearing all the flip-flops and the shift register, and then I am enabling the shift register. And after that, let me just load the value in the shift register. And after that, if I just run the simulation, then this is how the input bit stream will look like. So as you can see, the input bit stream is equal to 0001, 0010, 0100 and 1000. And for the given bit stream, as you can see, the output becomes 1 for the 3 times. That means indeed, this sequence detector works as an overlapping sequence detector which detects the 1001 sequence. So we can say that our designed circuit works properly as a sequence detector. So similarly, now let us see the simulation result for the non-overlapping sequence detector which can detect the 1001 sequence. So once again during the design, based on the Boolean expression that we got, this is the logic circuit for the non-overlapping detector. So here, this first flip-flop is the D0 flip-flop, but the second flip-flop is the D1 flip-flop. And once again, through a parallel in serial out shift register, the input bit stream is applied to the detector. And once again, the same sequence is applied to this detector. So for this non-overlapping type sequence detector, for the given bit stream, the output should become 1 only for the 2 times. So let us just run the simulation and let us validate our result. So once again, let me just zoom all the waveforms. So first, here I am clearing all the flip-flops and the shift register, and then after, I am enabling this shift register. And then after, by enabling this load input at the clock edge, I am loading the value inside the shift register. So after that, if I just run the simulation, then this will be the input bit stream to the sequence detector. And as you can see over here, the output becomes 1 only for the 2 times. So here the input bit stream is equal to 0001, 0010, 0100 and 1000. So as you can see, when the sequence detector detects the 1001, then the output of the detector becomes 1. But since it is a non-overlapping type detector, so after detecting the sequence, the detector will get reset. And therefore, once again the output of the detector will become 1 whenever it detects a new 1001 sequence. And therefore over here, the output of the detector becomes 1 only for the 2 times. That means indeed our detector works properly. So in this way, by following these steps, we can design any sequence detector, or in general, we can design any finite state machine. Now the sequence detector which we have designed over here is the Mealy machine. But similarly, we can also design the Moore machines. So in the next video, we will see that how to design the Moore type sequence detector. But I hope in this video you understood how to design any Mealy type FSM. So if you have any question or suggestions, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.